Welcome! In this session, we'll explore LeetCode problem number 2002, maximum product of the length of two palindromic subsequences. We'll dive into the problem requirements, analyze different approaches, and develop an efficient solution together. Let's get started. The goal of this problem is to find the maximum product of the lengths of two non-overlapping palindromic subsequences in a given string, S. To break this down, a subsequence is formed by deleting some or no characters from the string, while maintaining the order of the remaining characters. A string is considered palindromic if it reads the same forwards and backwards. For input, we are given a string S consisting of only lowercase English letters. The output is an integer, which represents the maximum product of the lengths of two subsequences that meet these conditions. For example, let's consider the string S equals icdampomp. Here, we can split S into two palindromic subsequences, ACA and PMPMP. The length of ACA is 3, and the length of PMPMP is 5, so the product of their lengths is 3 times 5, which equals 15. Another example is S equals axbabasexk. In this case, we can split the string into ababa and x. Both subsequences are palindromic, with lengths of 5 each, resulting in a product of 5 times 5, which equals 25. These examples demonstrate how the maximum product is calculated based on splitting the string into valid palindromic subsequences. Now, let's review the constraints and additional notes. First, the length of the input string S will always be between 2 and 12 characters. This ensures the problem is computationally manageable. Second, the string will only consist of lowercase English letters. A key detail to remember is that a subsequence is formed by deleting certain characters without changing the order of the remaining ones. Additionally, the two subsequences chosen must not overlap in the original string. Finally, for a subsequence to be palindromic, it must read the same backwards as it does forwards. These points are essential to solving the problem effectively. To approach the problem of finding the maximum product of the lengths of two palindromic subsequences, we need to start by considering how to identify these subsequences and ensure they are disjoint. The first method we could use is the brute force approach. Here, we generate all possible pairs of subsequences from the given string and check if both are palindromic. If they are, we ensure that the two subsequences are disjoint, meaning they do not share any characters. For each valid pair, we calculate the product of their lengths and keep track of the maximum product found. However, this approach quickly becomes infeasible for larger strings because the number of subsequences grows exponentially with the length of the string. Specifically, generating all subsequences takes 2 to the power of n, and comparing all pairs of these subsequences adds another layer of exponential complexity. Checking whether a subsequence is palindromic further adds n time per check. Altogether, this approach is computationally prohibitive for larger inputs. To address this, we look to more optimized approaches, such as using bit masking. Using the optimized bit masking approach, we represent subsequences with bit masks. A bit mask is a binary number where each bit corresponds to whether a character in the string is included in the subsequence. For example, if the string has 3 characters and the bit mask is 101, this represents including the first and third characters in the subsequence. This method allows us to efficiently iterate through all possible subsequences. For each bit mask, we check if the corresponding subsequence is palindromic. If it is, we store it for further analysis. Once we have a list of all palindromic subsequences, we compare all pairs to ensure they are disjoint. If they are, we calculate the product of their lengths and update the maximum product as needed. The complexity here is 2 to the power of n*n, which includes generating all subsequences and verifying their disjointness. While still exponential, this is more feasible for smaller strings, especially those of length up to 20. Another approach worth considering is dynamic programming, which precomputes whether substrings are palindromic, but it shares the same exponential complexity due to subsequence generation. Overall, bit masking strikes a good balance between clarity and performance. The reason we chose the optimized bit masking approach as our final strategy is its simplicity and efficiency. While the dynamic programming method also reduces the complexity of palindromic checks, it still requires exponential time to generate all subsequences. Bit masking, on the other hand, handles all necessary operations, subsequence generation, palindromic verification, and disjointness checks with minimal overhead, leveraging efficient bitwise operations. In terms of trade-offs, brute force provides a useful starting point for understanding the problem but is far too slow for practical use. Dynamic programming avoids redundant palindromic checks but doesn't significantly improve overall complexity. Bit masking simplifies the implementation while offering the best performance. The final complexity of O2 to the power of n asterisk n is manageable for n up to 20, which translates to around 1 million operations, well within the limits of most competitive programming scenarios. This makes the bit masking approach ideal for solving this problem within the given constraints. To solve this problem, we need to identify two non-overlapping palindromic subsequences from the given string, such that the product of their lengths is maximized. A subsequence, remember, is formed by deleting some or none of the characters from the string without rearranging the remaining ones. The challenge here is twofold: we must efficiently find palindromic subsequences and ensure that they don't overlap. The first step is to generate all possible subsequences of the string. We can use a bit masking technique to achieve this, where each bit mask represents a specific combination of characters. For a string of length n, there are 2n potential subsequences. For each bit mask, we include a character in the subsequence if the corresponding bit in the mask is set to 1. Once we have these subsequences, the next step is to check which of them are palindromes. A sequence qualifies as a palindrome if it reads the same forwards and backwards. We store only these palindromic subsequences along with their lengths, as they are the ones relevant for maximizing the product later on. After generating all palindromic subsequences, the next step is to evaluate all possible pairs of these subsequences. For each pair, we need to check if the subsequences are disjoint, meaning they don't share any characters from the original string. This can be efficiently done using the bit masks we generated earlier. By performing a bitwise operation on the masks of two subsequences, we can determine if they overlap. If the result is 0, the subsequences are disjoint. If the pair passes this check, we calculate the product of their lengths. This product represents the potential result for that pair. We then track the maximum product encountered during this process. Finally, once we've evaluated all valid pairs, we return the highest product recorded, giving us the solution to the problem. There are several important insights that make this algorithm both efficient and effective. First, bit masking is a powerful tool for generating all possible subsequences, as it provides a compact and systematic way to represent inclusion or exclusion of characters. Second, checking if a string is a palindrome is relatively efficient. It can be done in linear time with respect to the subsequence length. This ensures that we only focus on valid palindromic subsequences. Third, validating whether two subsequences are disjoint using bitwise operations is extremely fast, as it avoids the need for direct character-by-character comparisons. Additionally, we can optimize the process by filtering out shorter subsequences early on, as they are less likely to contribute to the maximum product. The use of these techniques not only reduces unnecessary computations but also ensures that our approach is scalable for moderately sized strings. Let's now analyze the complexity of this algorithm. Generating all subsequences using bit masking takes O2 to the power of n asterisk n, where n is the length of the string. This is because there are 2n subsequences, and processing each bit mask involves iterating through the string. Checking if a subsequence is a palindrome takes O(k), where k is the length of the subsequence. In the worst case, this leads to a total of O2 to the power of n asterisk n for all subsequences. For the pairwise comparison of palindromic subsequences, we check disjointness for each pair, which takes m squared, where m is the number of palindromic subsequences. However, the overall complexity remains dominated by the O2 to the power of n asterisk n term due to the exponential growth of subsequences. Finally, we must consider edge cases, such as an empty string, where the result is 0, or a single character string, which also yields 0 since no valid pairs exist. For strings with all identical characters or highly non-palindromic strings, the algorithm ensures efficiency by focusing only on palindromic and disjoint subsequences. These considerations make the approach robust and adaptable to a variety of scenarios. This Python implementation solves the problem of finding the maximum product of the lengths of two non-overlapping palindromic subsequences in a given string.
Here's the explanation.
1. Imports and helper function asterisk. The code begins by importing combinations from intertools, which isn't used explicitly but sets the foundation for combinatorial logic. A helper function is underscore palindrome is defined, which checks if a given string is a palindrome by comparing it to its reverse. 2. Initialization asterisk. The length of the string s is stored in n, and a variable max underscore product is initialized to 0 to keep track of the maximum product found. 3. Outer loop asterisk. The first loop iterates through all possible masks, subsets of indices, using a bitmask approach. A mask is an integer where each bit represents whether to include a character from the string in the subsequence. For each mask, a subsequence subsec1 is generated by including characters from s corresponding to the set bits in mask 1. For palindrome check for first subsequence asterisk. If subsec1 is not a palindrome, the code skips further processing for this mask. 5. Inner loop asterisk. The second loop iterates through all possible masks again to generate a second subsequence subsec2. The critical condition here is that mask 1 and mask 2 do not overlap, i.e., mask 1 and mask 2 equals 0. This ensures that the two subsequences are non-overlapping. 6. Palindrome check for second subsequence asterisk. If subsec2 is also a palindrome, the product of the lengths of subsec1 and subsec2 is calculated. If this product is greater than the current max underscore product, it updates max underscore product. 7. Final result asterisk. After all combinations have been considered, the function returns max underscore product as the result. This approach uses bitmasking efficiently to explore all possible subsequences and their combinations, checking for palindromic properties and ensuring disjoint subsequences. While the complexity is exponential due to the nature of the problem, this exhaustive search guarantees correctness for small to medium-sized input strings. Here, we begin implementing the solution in Java. First, we import the necessary utilities and define our class and method. The maxProduct method takes a string s as input, representing the sequence we are analyzing. We initialize n to store the length of the string and maxProduct to keep track of the maximum product of the lengths of two palindromic subsequences. Next, we declare a Boolean array is palindrome to pre-compute whether a subsequence, represented by its bitmask, is a palindrome. For each bitmask from 1 to 2 n1, we build the corresponding subsequence using a string builder. By checking the bits of the mask, we determine which characters from the string s are included in the subsequence. The helper function isPalindrome is then used to check if this constructed subsequence is a palindrome, and the result is stored in the isPalindrome array. After pre-computing, we iterate through all possible bitmasks for mask 1. If the subsequence represented by mask 1 is not a palindrome, we skip it. Otherwise, we calculate its length using integer.bitCount, which counts the number of set bits in the mask. This gives us the length of the first palindromic subsequence. Now, for each valid mask 1, we iterate through all possible bitmasks for mask 2. We ensure that the two subsequences do not overlap by checking if the bitwisen of mask 1 and mask 2 equals 0. If this condition is met and the subsequence represented by mask 2 is also a palindrome, we calculate its length using integer.bitCount. The product of the lengths of these two palindromic subsequences is then compared with the current max product, and we update max product if this product is greater. Finally, we return the maximum product after examining all valid pairs of subsequences. The helper method isPalindrome is implemented to check if a given string is a palindrome. It uses two pointers, left and right, to traverse the string from both ends and compare characters. If a mismatch is found, it returns false. If the pointers meet without finding a mismatch, the string is confirmed to be a palindrome, and the method returns true. This completes the implementation of our solution. Let's continue. Let's continue. Let's continue. Let's continue. To analyze the time complexity of this solution, let's start by understanding the brute force approach used to find the maximum product of the lengths of two non-overlapping palindromic subsequences. First, the outer loop iterates through all possible masks of length n, where n is the length of the input string. Each mask represents a unique combination of characters from the string, and since there are 2 n possible masks, the outer loop executes 2 n times. Next, for each mask generated by the outer loop, the inner loop also iterates through another set of 2n masks. This results in a total of 2n*2n, or 4n, iterations when considering both loops together. For each mask, a subsequence is generated by iterating through all n characters of the string and checking the mask, which takes n time. This is the basic setup for how the brute force approach iterates through all possible pairs of subsequences. After generating a subsequence, the solution includes a step to check if that subsequence is a palindrome. To determine if a string of length k is a palindrome, the algorithm compares characters from the beginning and end of the string, moving inward. This process takes k time, where k is the length of the subsequence. In the worst-case scenario, where the subsequence includes all n characters of the string, this operation takes n time. When combining these steps, the total time complexity can now be derived. The two nested loops contribute 4 to the power of n iterations, and for each pair of masks, subsequence generation and palindrome checking together contribute n plus n, which simplifies to n. Multiplying these factors, the overall time complexity of the solution is 4 to the power of n*n, which reflects the exponential growth in the number of subsequences as the length of the input string increases.
Now focusing on space complexity, there are three main contributors to consider.
First, the is_palindrome function uses a recursive approach, which requires space on the call stack proportional to the length of the subsequence being checked. In the worst case, where the subsequence length is equal to n, the recursion stack contributes n space.
Second, for each mask, the algorithm generates a subsequence.
While this requires n space in the worst case, the storage is reused for every new mask, meaning it does not accumulate. Finally, other variables used in the algorithm, such as the masks, the maximum product, and loop counters, require only constant space, or 1. When combining these factors, the overall space complexity is dominated by the recursion stack and the temporary storage for subsequences, both of which are bounded by n. Therefore, the total space complexity of the solution is n. Let's compare this brute force approach to other possible methods. A completely naive solution would involve generating all possible pairs of subsequences from the string and checking which pairs are palindromic. Since the number of subsequences in a string of length n is 2n, generating all pairs would require 2 to the power of n, 2, which simplifies to 4 to the power of n, operations. Additionally, checking whether each pair is palindromic would add another n factor, resulting in a final time complexity of 4 to the power of n*n. This is the same as the current solution, but the current implementation uses bit masking to systematically generate subsequences, which is more structured.
However, optimizations are possible. For example, by using dynamic programming or memoization, we could store intermediate results and avoid redundant palindrome checks.
These techniques could significantly reduce the computational overhead and improve efficiency.
Finally, let's break down the time complexity into best, average, and worst-case scenarios.
In the best case, the input string is very small, such as n equals 1 or n equals 2.
Here, the algorithm quickly terminates, though the time complexity remains exponential with respect to n.
In the average case, the algorithm generates 4n masks and performs palindrome checks as described, resulting in a time complexity of 4 to the power of n*n. The worst case occurs when n is large, maximizing the number of iterations in palindrome checks. Regardless of the input size, the derived time complexity remains 4 to the power of n*n.
Mathematically, this is explained by the nested loops iterating 2n times each, resulting in 4n iterations.
For each pair of masks, subsequence generation and palindrome checks add n time, leading to the overall time complexity of 4 to the power of n*n. As for space complexity, it is consistently dominated by subsequence storage and recursion stack usage, which are bounded by n, making the solution's space complexity n in all cases.
One of the most common mistakes when solving this problem is failing to ensure that the two palindromic subsequences are non-overlapping.
If the subsequences share indices, it violates the constraints of the problem and leads to incorrect results. To address this, you can use techniques like bit masking or explicitly track the indices to guarantee that the subsequences are disjoint. Another frequent pitfall is inefficient palindrome checking. If you directly verify whether a subsequence is a palindrome during every iteration, it can become very resource-intensive, especially for longer strings.
A more efficient approach is to pre-compute whether substrings are palindromes using dynamic programming or memoization, which avoids redundant checks.
Lastly, edge cases are often overlooked, particularly for very short strings like those of length 1 or 2. These can cause runtime errors or incorrect outputs. To handle this, you should include specific conditions upfront, such as directly returning 0 for a string of length 1, since no valid pair of subsequences can be formed in that case.
Another issue arises during subsequence generation.
If subsequences are generated incorrectly either by missing certain combinations or duplicating indices, it can lead to incomplete or redundant solutions.
A systematic method, such as bit masking or recursion, ensures that all valid combinations are considered. Additionally, not optimizing for large inputs is a major source of inefficiency. For example, solutions with a time complexity of 2 to the power of n*n can easily time out when the string length reaches 20 or more. This often happens when all subsequences are generated without pruning invalid ones. To address this, you can optimize by pruning subsequences that are invalid early in the process and by limiting unnecessary computations. These optimizations are crucial for ensuring your solution runs efficiently on larger test cases. From an interview perspective, this problem highlights a key pattern involving two major components: generating subsequences and checking if they are palindromes. To solve it efficiently, you need to balance these steps in a way that minimizes redundant work. One effective approach is to use bit masking for subsequence generation and pre-compute palindromicity using a helper function. This combination ensures that your solution is both correct and fast. During an interview, it's important to clearly explain how you handle non-overlapping subsequences and optimize palindrome checks. Be prepared to discuss your trade-offs between time complexity and implementation difficulty. Common follow-up questions might include extending the problem to 3 palindromic subsequences or scaling the solution for larger input sizes, such as when the string length exceeds 20. Demonstrating how you would adapt your approach in these scenarios can leave a strong impression on the interviewer. There are several related problems that can help you build a strong foundation for solving this one. For instance, LeetCode 647 focuses on counting palindromic substrings, which is useful for understanding basic palindrome detection techniques. LeetCode 516, on the other hand, centers on finding the length of the longest palindromic subsequence, which can help you develop intuition for using dynamic programming in palindrome-related problems. LeetCode 131 explores partitioning a string into palindromic substrings, making it a related combinatorial problem that emphasizes dividing strings strategically. Lastly, LeetCode 5 deals with finding the longest palindromic substring. This problem is particularly helpful for refining your methods for detecting palindromes efficiently. By studying these related problems, you can strengthen your understanding of the core techniques involved and better prepare for variations of the maximum product problem. There are multiple approaches to solving this problem, each with its own trade-offs. The brute force approach involves generating all possible pairs of subsequences and checking if each pair consists of palindromes. While this method is conceptually simple, it has a time complexity of 2 to the power of n*n, which makes it impractical for large strings. A more efficient alternative is to use dynamic programming combined with bit masking. Here, bit masking helps systematically generate subsequences, while a DP table pre-computes palindromicity. This approach, while more complex to implement, allows for pruning invalid pairs early and can significantly reduce redundant computations, offering better performance. Another option is recursive backtracking, where you explore all subsequences while ensuring they remain disjoint. By combining this with memoization for palindrome checks, you can streamline the process. However, this method may still be slower than bit masking for larger inputs. Choosing the right approach depends on the context, but understanding these alternatives helps you adapt to different constraints and scenarios effectively. That's a wrap. We've covered how to solve the maximum product of the length of 2 palindromic subsequences problem, highlighting the key steps and takeaways. Thanks for joining me today. Be sure to like, subscribe, and check out other videos for more algorithm insights. See you next time. That's the end of this tutorial.
I hope you found this explanation helpful for understanding the solution to this LeetCode problem.
If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!